Jai Hind, myself Shukla, Assistant Professor in Computer Science Engineering Department at AKGEC Engineering College, Ghaziabad. Today I will discuss a topic, Combinators, which is very important for the third semester students of BTech. I will cover today a combinatorics introduction, counting techniques, and pigeonhole principle. Now, combinatorics introduction, permutation and combination. Permutation. What is permutation? Permutation is basically an arrangement of R things out of N things. A permutation of N objects taken R at a time. A permutation of N objects taken R at a time is an arrangement of R of the objects, and it is represented by NPR. Permutation of R objects taken at a time out of N objects, and it can be written as factorial N divided by factorial N minus R. For example, consider the three letters A, B, C. The arrangement of the letters A, B, C taken two at a time is 3p2. 3p2. Out of three letters, two are taken at a time. Arrangement of two is taken at a time, that is 3p2, and it will be written as factorial 3 divided by factorial 3 minus 2. That is factorial 3 divided by factorial 1. It means 3 into 2 into factorial 1 divided by factorial 1. Yani there will be 6 ways. So what are the ways? So three letters A, B, C taken two at a time. So what will be the possible arrangement? That is AB, BA, AB, BA, AC, CA, BC and CB. So total 6 arrangements are there. 6 arrangements are there. This can be done by this way also. Like two objects are taken at a time and there are three letters. So what will be the possible arrangement? What will be the possible way of choosing one letter from the three? That is 3. And what will be the possible ways of choosing this if repetition is not allowed? Distinct arrangement, that is into 2. Yani ki 6 ways are there. 6 ways are there. So permutation is applicable when ordering sequencing of numbers या elements या objects are important. So there are the 6 ways. So number of R permutation without repetition. The number of R permutation of N objects is PNR. That is N minus 1, N minus 2, N minus R plus 1. And it can be also written as factorial R divided by factorial N minus R. For example, how many words of 3 distinct letters can be formed from the letters of the word land? So we have to make 3 distinct letters. 3 distinct letters out of the 4 letters. Land having 4 distinct letters, L, A, N, D. 4 letters are there. And we have to make 3 distinct letters. We have to form 3 distinct letters. So what will be the possible arrangement? So this can be chosen in 4 ways. This place can be occupied by 3 ways. And this place can be occupied by 2 ways. So total number of ways, a total number of arrangement will be 4 into 3, 12 into 2, that is 24. In a simple way, we can also do like out of 4, 3 things are arranged, yani 4p3. That is factorial 4 divided by factorial 4 minus 3, that is factorial 4 divided by factorial 1 equal to 4 into 3 into 2 into factorial 1 divided by factorial 1, that is 24 wage. 24 wage. Now permutation with like elements. The number of permutation of n objects of which q1 are alike, q2 are alike and qr are alike is given by factorial n divided by factorial q1 into factorial q2 into factorial qr. For example, if there are 4 blacks, 3 greens and 5 red balls, in how many ways can they be arranged in a row? So, total number of balls will be n, first calculate, that is 4 black plus 3 green plus 5 red, that is 12 total balls are there, out of which 4 balls are black same type, 3 are green of same type and 5 are red of same type. So total number of arrangement will be, total number of permutation will be factorial r 12, that is n, divided by factorial 4 into factorial 3 into factorial 5. Because total number of balls will be 4 plus 3 plus 5, that is 12, out of which 4 are of same type, that is black, so it will be coming in denominator of same type, that is q1, 3 are of same type, that is factorial 3 here, and 5 are red type of same type, that is factorial 5, and after calculation it will be coming 27720. So total number of arrangement will be 27,720. Circular permutation. Circular permutation, a circular permutation of n objects is an arrangement of the objects around a circle. For example, suppose n distinct objects are there and we have to arrange in a circular way. So how many total permutations are there in this case? So what we will do that, first of all, out of n objects, we have taken only one object and fixed the position. One object, out of n objects, we have taken only one object, and rest n minus 1 objects we can arrange this position. This position can be arranged by n minus 1 ways. This position can be arranged n minus 2 ways. This position can be arranged n minus 3 ways. This n minus 4, this and so on, n minus r. So what we will do here, out of n objects, we have taken one object and fixed the position, and rest n minus 1, this place will be occupied by n minus 1, this place will be occupied by n minus 2, n minus 3, n minus 4, n minus 5 till last one. So what we will get, that is 1 into 2 into 3 into dot 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 n minus 1. So total number of permutation in this case will be factorial n minus 1. So n objects can be arranged in a circular permutation by factorial n minus 1. For example, in how many ways can a party of 9 persons arrange themselves around a circular table? So total number of person is 9. So the value of n equal to 9. and we have to arrange in a circular permutation. So fix one objects, one person at this position, and rest 8 person can be arranged in factorial 8 ways. So factorial n minus 1, that is 9 minus 1 is equal to factorial 8 ways we can permute, we can arrange 9 person in a circular fashion. In how many ways, second example we can see, in how many ways 5 gents and 4 ladies dine at a round table if no 2 ladies are to sit together. So first what we do, first 5 agents we have to arrange in a circular fashion. We have to do arrangement 5 gents. So 5 gents can be arranged in a circular fashion, factorial 5 minus 1, that is factorial 4 ways. So gents G, 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 G and G. So fix one as a gents position and rest it can be done in factorial 5 ways. And in between we have to arrange ladies so that no ladies can sit together. So there are 1, 2, 3, 4, 5. 5 places are there where we can arrange 4 ladies. So total number of permutation will be 5p4. So 5p4 means factorial 5 divided by factorial 5 minus 4, that is 1. It means 5 into 4 into 3 into 2, that is 120. 120, and this man can be arranged in factorial 4. It means 4 into 3 into 2 into 1, that is 24. So total number of permutation will be 24 into 120, that is 2880. That is 2880. So this is the application of circular permutation. Both example we see the example of circular permutation. Now 12 persons are made to sit around a round table. Find the number of ways they can sit such that the two specified are not together. In this case 12 persons, total number of persons are 12. So how many possible arrangements are there? 12 persons, it means with factorial n minus 1, that is factorial 12 minus 1, that is factorial 11. 11 ways we can do arrangement in a circular fashion. 11 ways. The total number of ways in which two specified persons are together. Two specified persons are together. So what we will do, two persons we will consider as a unit. If we consider as a one unit, so we will consider 11 because total persons are 12. So 10 and 2 are 10 are different here and 2 are here. So these two are taken as a one unit. So total number of persons in this case will be counted as a 11. And 11 person can arrange in a circular way, circular fashion will be factorial 10. Factorial n minus 1 is applicable. And these two person can sit in factorial 2 ways. We can alter the position. So factorial 2 is the arrangement of these two persons. So total number of permutation in this case will be factorial 2 into factorial 10. So this is factorial 2 into factorial 10. So the required number of sitting arrangement in which two specified persons are not together is factorial 11 minus factorial 2 into factorial 10. This. So factorial 10 will be written as, this will be written as 11 into factorial 5. This will be written as 11 into factorial 10 minus factorial 2 into factorial 10. Take factorial 10 as a common. This will be 11 and minus factorial will be treated as a 2. So this is factorial 10 into 9, yani 9 factorial 10. This is the right answer. This is the right answer. Now combination. What is combination? A combination of n objects taken R at a time is an unordered selection. While in a combination, while in a permutation, n objects, out of n objects, R objects are taken and the selection is ordered. Sequencing is important. But here, order is not important. So a combination of n objects taken R at a time is an ordered selection and it is given by NCR. Combination of R objects out of n objects, where sequencing is not important, ordering is not important, and is given by factorial n divided by factorial R into factorial n minus R, by this way, like this way. See the example. A farmer purchased 3 cows, 2 pigs and 4 hens from a man who has 6 cows, 5 pigs and 8 hens. Find the number n of the choice that the farmer has. So out of 6 cows, 3 are chosen. So this can be achieved by 6C3. Again, out of 5 pigs, 2 are chosen, 5C2. Again, out of 8 hens, 4 are chosen, 8C4. And multiply this, we will get 14000. So total number of selection, a total number of choice that the farmer has, 14,000. Basic counting principle. Now come on the basic counting principle. So basic counting principle, assume some events E can occur in M ways. Suppose an event E can occur in M ways and event F can occur in N ways. And both events are exclusive, not depend on the others. In this case, the event E or F can occur in M plus N ways. In general, if there are n events and no 2 events occur simultaneously, then the events can occur in n1 plus n2 plus ... n ways. For example, if 8 male professors and 5 female professors teaching DBMS, then the student can choose professors in 8 plus 5 ways, that is 13 ways. Another example, see, how many ways can we get a sum of 7 or 11 when 2 distributable dice are rolled? So 2 distributable dice are rolled and coming 7 and 11, 7 are 11. So the order pairs are, for coming sum 7 when 2 dice are thrown, that is 1 6, 2 5, 3 4, 4 3, 5 2 and 6 1. These are the order pairs and these are the distinct, and the sum is 7. So total number is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there are 6 ways to obtain the same 7. And there are 2 ways to obtain the sum 11, that is 6, 5 and 5, 6. So total number of ways in which we get sum 7 or 11 is 6 ways of coming 7 and 2 ways are coming 11. So total number of ways of coming 7 or 11 is 6 plus 2, that is 8 ways. So here some rules, basic counting, some rules is going to apply it. Product rule. Suppose there is an event E which can occur in n ways, and independent of this event there is a second event F can occur in n ways, then the combination of E and F can occur in m into n ways, mn ways. For example, in a class there are 4 boys and 10 girls. If a boy and a girl have to be chosen for the class monitor, the students can choose monitor in 4 boys are there, so 4 ways, and 10 girls are there, so 10 ways. Multiply this because product rule is going to apply it here, so 40 ways. Another example, see here, in how many different ways one can answer all the question of true false test consisting of 4 questions. So 4 questions are there. So true and false, 2 possibilities are there. So possibility is 2, again 2, 2 and 2. So product rule is going to apply. So total number of ways is 16. Another example we can see, find the number n of the license plate that can be made when each plate contains 2 distinct letters followed by 3 different digits. So we have to make a licensee plate. Each plate contains 2 distinct letters followed by 3 different digits. So how many possible ways are there? So this can be filled by 26 alphabets are there. So this position can be chosen by 26 ways. Again this position can be chosen by 25 ways because repetition is not allowed, and we have to need a distinct letters. So 26 into 25. So these 2 are occupied by the alphabets followed by 3 distinct digits. So total 10 digits are there. So this place will be occupied by 10 digits. Again this will be occupied by 9 and this will be occupied by 8. If repetition is not allowed, if we require a distinct letters followed by the 3 distinct digits. Now if anybody asks how many possible ways are there if repetition is allowed, so in this case this position can be chosen 26 ways, this can be chosen 26 ways, this place can be chosen in 10 ways, this can also be 10 ways, this can also be 10 ways. So by this way total number of ways will be this if repetition is allowed. Next, a pigeonhole principle. So pigeonhole principle, in 1834 German mathematician Peter Gustav Dirichlet stated a principle which is called a drawer principle and known as the pigeonhole principle. Pigeonhole it states that if there are n pigeons and n pigeonhole and m is greater than n, m pigeons and n pigeonhole, and m is greater than n, it means pigeons are greater than the pigeonhole, then there must be at least one pigeonhole which have more than one pigeons. This is the pigeonhole principle. For example, if there are 13 professors, then there must be at least two professors, more than one professors which having same born, same month of born. This is, for example, see this example. If 10 peoples are chosen in any way, so that at least two of them will have been born on the same day. This type of questions. Suppose a department contains 30 professors, then two of the professors were born in the same month. This is the pigeonhole principle. So 13 professors are there. So this is the pigeons, m equal to 30, right? And pigeonholes are n, that is in a year there are 12 months. So this will be 12. 12 is considered as a pigeonhole. So if m is greater than n, then there must be at least one pigeonhole which have more than one pigeons. It means there will be a 1 month which having born more than one professors. So this is the pigeonhole principle. Another example we see, find the minimum number of elements that one need to take from the set S equal to 1, 2, 3 up to 9 to be sure that two of the numbers add up to 10. So there is a set and elements are from 1 to 9 and sum should be 10. Two of the numbers, sum of the two of the numbers will be 10. So the pigeonhole are 1, 9 because the sum is 10, 2, 8 and all the elements are the elements of set 1, 9, 2, 8, 3, 7, 4, 6 and 5, 5. So there are 5 pigeonhole, n equal to 5. So pigeons are n plus 1, one more than the pigeonhole, n plus 1. So thus any choice of 6 elements. So pigeons will be n plus 1, that is 5 plus 1, that is 6. So any choice of 6 elements, yani pigeons of S will guarantee that two of the numbers add up to 10. Generalized pigeonhole principle. If n pigeonholes are occupied by kn plus 1 or more pigeons, where k is a positive integer, then at least one pigeonhole is occupied by k plus 1 or more pigeons. For example, in the previous examples, we see 13 professors. So in this case, kn plus 1 equal to 13. N equal to pigeonhole. So n equal to 12 month. That is in a year, 12 months are there. So put this value k into n, 12 plus 1 equal to 13. So k into 12 equal to 12. So k equal to 1. So then at least one pigeonhole is occupied by k plus 1. K plus 1, k is equal to 1. So k plus 1 equal to 2. So at least one pigeonhole is occupied by 2 or more pigeons. So k equal to 2, hence among any kn plus 1, next question, again the application of this. Find the minimum number of students in a class to be sure that 3 of them are born in the same month. Okay, so see this. 3 of them are born in the same month. So 3 means k plus 1 equal to 3. So here k equal to 2. And pigeonhole are n equal to 12. So minimum number of students in a class to be sure that 3 of them are born in the same month will be kn plus 1. Kn plus 1. That is 2 into 12 plus 1 equal to 25. So this will be 25. So minimum number of students, that is 25 in a class, to be sure that 3 of them are born in the same month. In worst case, what will be there? Suppose 12 students can born in a different months in worst situation. Again 12 students can born in a different months, then 24. Then 25th students will be born in 1 month, any month. So there will be the minimum number of students in a class to be so that 3 of them, 3 means 25 students if we get, then the possibility, this is the minimum number, we can say 3 of them can born in the same month. Again, example of pigeonhole principle. Minimum number of n of the integers to be selected from s equal to 1 to 9 so that the sum of 2 of the integer is even. So we know that the sum of the 2 integer is even. This is possible only when even plus even equal to even and odd plus odd equal to even. There are 2 possibilities. So there are 2 pigeonholes. So sum of the even integer of the 2 odd integer is even. Consider the subsets. So we take 1 to 9 from the set S. We take a subsets as odd numbers and subset as even numbers, because sum of the odd is also even and sum of the even is also even. So we take, we bifurcate, we divide into the 2 parts, 2 pigeonholes, 1, 3, 5, 7, 9 and 2, 4, 6, 8. So if 2 pigeonholes are there, so there will be n plus 1, one more. So n equal to 3. So n equal to 3 pigeons are there, minimum. So minimum number of integers to be selected. So there will be a 3 to be selected from S so that the sum of the 2 of the integers is even. The difference of the 2 of the n integer is 5. So we take 5 subsets as a 1, 6, 2, 7, 3, 8, 4, 9 and 5 as a pigeonhole. And if 5 pigeonholes are there, then n plus 1 pigeons. It means 6 will guarantee that 2 integers will belongs to one of the subsets and the difference will be 5. Suppose there are 10 pigeons and there are 9 pigeonholes. See another example. If a bag contains 10 red marbles, 10 white marbles and 10 blue marbles. what is the minimum number of marbles you have to choose randomly from the bag to ensure that we get 4 marbles of the same color. So apply pigeonhole principle. Here n equal to 3. 3 means number of colors red, white and blue. So n equal to 3. Number of marbles, that is pigeons equal to k plus 1. That is one more pigeonhole. Pigeons are one more than the pigeonholes, that is 4. And this is what? K. We can say this is K. Yeah, N. But so minimum number of marbles required will be Kn plus 1. This is the generalized principle, pigeonhole principle. So this will be K, that is 4 into N 3 plus 1. So 13. So this value is coming 13. So 13. So K equal to 3 here. K plus 1 equal to 4. So K equal to 3. So 3 into 3 plus 1, that is 10. So 10. So 10, 3 red, 3 white and 3 blue plus 1 red or white or blue equal to 10. So total number of, thank you.